So one of the things I meant to mention in the last lesson video is the fact that I am saving, just like I've been doing most of the school year, I am saving the completed flip charts, and they'll be the last thing in your playlist. So if you need to go back to lesson 1 from this week and see the filled out notes, they're there. Okay? So, sorry, you're going to hear my dog in the background too. Anyway, so in this drill, we're talking, and it might not seem related, but hopefully we'll get to the point where you will see the relationship. It says the distance Mr. Tucci must travel to get to work is 20 miles, and his average speed is 5 miles per hour. How long does it take him to get to school? I don't know how many of you are familiar with this formula. I know we use it in physics. I don't know where everybody else is, but the formula that we use when we're talking about this kind of thing is that distance equals rate times time. But because what we're actually looking for is the time, that's the question, we're going to divide both sides by the r value. So we're going to use distance divided by rate equals the time. Okay, so that's the formula we're going to use for the warm-up. So in this specific case, he was 20 miles away, and his rate was 5 miles per hour, and that should equal our time. So when we do that one, what we're going to get is 4 hours. Hopefully that is not a drive he has to make. 5 miles an hour, that's kind of crazy, unless you're in a major backup. So looking at the second one, what if he increased his speed to 10 miles an hour? We're going to use that same formulation there. We're going to do 20, but instead of dividing by the rate or the speed of 5, we're going to divide by our new one, which is 10. So time is going to equal 2 hours. It's a little better, but still not worth the drive probably. You can find something closer. The last one he's going to do is at a 30 mile an hour rate. So when we take our 20 and divide it by our 30 to get our time, what we end up getting is 2/3 basically, which is 0.67. Now that's 0.67. It's not 67 minutes. We can't just simply transfer decimals to minutes. We actually have to translate 60 minutes in every hour. So what I'm doing right now, just to give you an idea of minutes, I'm taking the 0.67 and multiplying it by the 60 minutes that are in an hour. So 0.67 times my 60 would actually be 40.2 minutes. And again, just like that wasn't 67 minutes, that 0.2 or 2/10 is not 2 seconds. We'd have to do that conversion also. So it's a little over 40 minutes at 30 miles an hour. Okay, we're going to hold on to this information because we're actually going to use these 3 answers that we just calculated in the next couple slides. Okay, so in this lesson, remember, I'm not going to remind you at this point, but for the rest of the thing, but if you are not done and you hear that, you know that I'm about to go on to the next one, just pause the video. Okay, I'm not there to say, okay, I'll go back a slide or two. Just pause the video. All right, so today you're working on characteristics of specifically inverse functions. We're looking at inverse functions. Okay, and what that means is you'll notice these two down here. These are our parent functions of them. In both of them, our variable x is in the denominator. This is y equals some number over x to the first power, and this is y equals some number over x squared. Okay, and we're going to look at those two equations and the graphs of them and talk about all their characteristics that go with it. But first, I want to kind of go a little further with this distance rate times time that we started with in the warm-up. So if I'm looking at this, if his x is 5 miles an hour, what I did was I took the 20 and I divided by whatever the x was. Okay, so in the warm-up, we got that he would go 4 hours when he was going 5 miles an hour. We got that he could go 2 hours when he was at 10 miles an hour. Okay, So you can do that same calculation with each one of these different speeds. So hopefully you can see 20 is a pretty easy. That's going to take us, he's going to go for 1 hour. Okay, that's 1 1/3 is the 15. And now it's actually going to start getting less than 1. Okay, it's going to take him less than 1 hour. So for this one, for 25, it's 8/10 of an hour. For 30, that should be 0.67, right? 2/3 of an hour. 35 is 0.57. 40 miles per hour, which is kind of an average speed for the area we're in, would take him a half an hour or 30 minutes. That's pretty reasonable. 45 miles an hour, 50 miles an hour. It doesn't seem to be reducing as fast as it did up here, is it? So when I go from 0.44 to 0.4, I'm only taking 0.04 off. Where up here I took 2 off, 2 holes. Okay, and if he goes 60 miles an hour, besides getting a ticket, he's going to be driving for 1/3 of an hour, which is only 20 minutes. And he gets all the way down here to 80 miles an hour. It's only going to take him 15 minutes. Now, going through Bel Air and traveling on 24, I'm hoping he's not driving at 80 miles an hour. All right, so these are the points that we're going to deal with. And we want to try and put them on this graph right here. Okay, so you can either, flip back and forth and check those numbers and graph them, or you could actually graph this function in Desmos and see what the graph is that it gets you. I'm going to go ahead and plot some of the basic points. I'm going to plot 5, 4, 20, and 1. Let me go do those. So 5 over to 5 and up to 4. I don't have a pen right now. That could be a problem. That would be a dot right there. I go over to 20. It took me to 1. This doesn't seem very lined up, does it? I think I know what happened. Excuse me. These are not correct values. I'm going to cover this up. I think I enlarged something and it didn't carry over to the numbers. Excuse me. So I'm just going to write over them. All right. So if we make this 0.5, and then this is 1, that would make this 2, that would make this 3, and that would make that 4. That's going to work better for me. All right. So 20 took us up to 1. Okay. If I go back and look at another one, that's a pretty easy one to graph. 40 is at 0.5. So I'll come over here to 40 and go up to 0.5. And you guys didn't catch my mistake, or I didn't hear you. I put the 20 at the 1/2 instead. I don't like flipping back and forth. You can tell. Let's see if there's another easy one to graph. I could graph 80 and 1/4. So I go over to 80 and up to 1/4, which is way down here. So if I actually go in and I work on connecting these, this curve is going to look like this. Okay. And what we just graphed was our relationship D equals 20 divided by the rate. Okay. And we only have positive numbers here because he can't go negative speed. He can't go negative distance. All those things still apply. This is actually what one of our inverse graphs looks like, but only half of what it looks like. They both have the same first quadrant. Remember, I just showed you the y equals k over x and y equals k over x squared. So they both have the same first quadrant. They're both in 2 quadrants. It's which second quadrant that they have that we want to take a look at and describe all of those characteristics. All right, so there's my graph. So some inverse relationships. What this means, if we had a direct relationship on something, that would mean that as I increased my x value, my y value would increase. So for instance, if you get paid by the hour where you work, as you increase the number of hours you work, you increase how much you get paid. Okay? As I increase my food intake, I increase my weight. Those are a direct relationship. An inverse relationship is one where they go opposite. As one of them increases, the other one would decrease. So basically, this is an inverse relationship when we think about driving. So as I increase my speed, I'm actually going to decrease the time it takes me to travel a specific distance. Okay. As I have a stack of paper sitting on my desk, plain paper, and I'm going to make copies. As I increase the number of copies I make, I decrease the number of blank paper I have. Okay. So there's an inverse relationship there. All right. So you can see the first one that we talk about, this is all inverse. It doesn't matter what the exponent is as we increase this bottom, this denominator in the function, what it's doing is it's actually making it smaller and smaller. Okay. If you just think about basic fractions, we can go from 1/2 to 1/3 to 1/4. They keep getting smaller and smaller. 1/5. So I didn't even increase the numerator. I just kept increasing the denominator, and the overall result keeps getting smaller and smaller decimals. Another example of this, and this might be something you talked about in chemistry, is the volume of a gas kept at a specific temperature varies inversely with the pressure. So basically, if I increase the volume, I would be decreasing the pressure. If I increase the pressure, I would be decreasing the volume. So that's all we talk about when we're talking about inverse relationships, is that as one rises, the other one falls. All right, so here's some look at some inverse relationships again. So we've got a balance on a seesaw here. Basically, this is like a balance scale, and we want to be able to place things across this scale. And what it says is the distance a person is from the fulcrum. That's this point where the seesaw actually pivots on, right? That's the fulcrum. So the distance the person is from the fulcrum, so they're 2 spaces away, is inversely proportional to his or her weight. So I want to increase the distance if I have a lighter person. So this person is 2 blocks in weight, and this person is 1 block in weight. Notice, as I decreased the weight of the person, I had to increase how far it went from the fulcrum. As I increased the weight, I actually decreased. I can't do this backwards. I actually decreased. I told you I couldn't do backwards. I didn't want to go all the way over there. I'll do it from here. I actually decreased the distance from the fulcrum. Okay. So if I decrease the weight, I increase the distance. If I decrease the distance, I increase the weight. That's why, if you're talking about a father and son on a seesaw together, the father should actually come closer to the center of the seesaw so that they can actually balance better, because he's much heavier than his son. And so that way the boy's actually going to be able to go up and down and not just get stuck in the up position. The intensity of a light produced by light source varies inversely as the square. Now this adds a different dimension onto us, as the square of the distance from the source. Okay, so basically I have a light bulb, and the closer I get to that light bulb, so I'm decreasing my distance, the more intense the light gets. Well, that makes sense. And it actually is a lot faster of a growth or a decay because of that squaring. All right, so we're going to be making a lot of graphs. So when you draw your graphs today, I want you to use a scale of 0.5. What that means is that every one of your blocks is worth 0.5. So if that's 0.5 here, then there's your 1, and there's your 2, and there's your 3. Okay, so I'm pretty sure every graph we're going to use today is going to use a scale of 0.5 in all directions. Okay, if it's going to change, I'll tell you otherwise. All right, so we're going to be graphing a lot of these, so you might want to have Desmos pulled up in the background, because that's the easiest way to just look at a graph instead of having to plot the points ourselves, right? All right. So these are all of the equations we're going to graph today. So if you wanted to, you could take a screenshot of this, take a picture on your phone, something, so you didn't have to keep flipping back and forth in between. We're going to look at these first 2 graphs and then these second 2 graphs. Basically, look at the pairings that I've done. And you can notice that the bottom of the first 2 is to the first power, and the top is a positive number. When we go to the second set, the bottom is still going to be to the first power, but we are going to have changed the numerator to a negative. We get to this one, we have a positive numerator, but the bottom is squared, the denominator is squared. And then the last set we're going to look at is when we take and make the numerator negative with a squared denominator. Okay? All right, so here's our very first one. We're going to go ahead and graph this. You could just put this in your calculator in the Desmos and get the Desmos to graph it for you. You probably only want to go to -5 to 5 in the x direction and -5 to 5 in the y direction. That'll probably get you the scale of 0.5. While you're setting that up, I'm going to go ahead and plot the points that I already found for these. So I have 2.5, negative 2.5, 1, 2.5, and down to 0.4, which is right about there. Okay, and a positive 2, I think that was supposed to be a negative in that. That is. So a negative 2 gets me to negative 0.5, which is here. A negative 1.5 takes me to 2/3, to 0.66, which is right there. A negative 1/2, I just skipped something in there, didn't I? Oh yeah, I skipped negative 1. Negative 1 takes me to negative 1, which would be there. Negative 0.5 would take me to negative 2. So we're seeing this branch. You don't necessarily have to finish this connection as we go, like I'm showing, but that is the connection on there. And then I can do the upper branch, which is, you can see it's all positive numbers, so it'll fall up in the first quadrant. This is not the variable x. This is actually meaning undefined in that spot. So there is no point on the y-axis whatsoever. There's no point on the x-axis. So I go over to 0.5 and up to 2. I go over to 1 and up to 1. 1.5 is 0.67. 2 is at 0.5. And then 0.4. So this is the parent function, the basic function 1 over x. Okay? So when we were doing that distance traveled in the warm-up, we were seeing part of this graph. We just weren't seeing this negative part of the graph. Okay? So an inverse relationship has two branches. That's what those are called. So two branches. In this specific one, I have asymptotes. Remember, asymptotes are the lines that the graph appears to approach but never touches. And it's going to be the y-axis, which is x equals 0, and the x-axis, which is y equals 0. Okay, those are the places that it never touches. What else? I can talk about the domain. Okay, so the domain, the x values is, well, I have negatives, I have positive, but it never touches 0. So the domain is x does not equal 0. And the range falls kind of the same way. I have positive y values, I have negative y values, but I don't have anything hitting this axis here, so y cannot equal 0. So those are the kind of questions we're going to be asking. So when we go to graph the next one, which is 4 over x, we can see what's going to happen to these points. Now, it's set up the same way. It's a positive number over x to the first power. So we should see similar graph, but we're going to check out and see what happens when we increase the numerator. Okay? So we're going to graph these points for 4 over x. So again, I'm counting by 0.5s all the way around. So we go negative 2.5, 1, 2.5, and it's negative 1.6. So that puts my point there. We have, again, that's supposed to be a negative 2, 1, 2, 1, 2, negative 1.5, 1.5 goes to negative 4, that's negative 2, 3, and 4. I'm sorry, 2.6, 2, 6. What was negative 1 was negative 4. And that pretty much takes us off of our piece of graph paper. I really can't even graph that 0.5 at negative 8. Okay, so it looks like that in that branch. Then I'm going to go over to 1 and up to 4. I believe this is 4. 1, 2, 3, 4. Yep. And then 1.5 goes to 2.6. and 2 goes to 2. 1, 2 goes to 2. And 2.5 goes to 1.6. So basically, comparing the two graphs we have here, I still have the two branches. I still have the same asymptotes, still have the same domain. I still have the same range. Increasing the numerator caused a stretch or expansion from the origin. Because if we go back real quick and look at the one before this, it was there. See how it was closer to the origin? And then there. And it stretched it away from the origin. Okay? All right. Now we're going to look at making it negative. Let's see what happens. Can you make a prediction? Okay, keep that prediction in your head. Let's see if we can figure out what happens. There's the values I ended up calculating from my calculator. You could just type that into Desmos and see what the graph looks like. I'm going to graph it here on the screen. So negative 2.5 gets me up to 0.4, which is right about there. And again, this should be negative 2. So negative 2 gets me to positive 0.5. Negative 1.5 is 2/3. Negative 1 is positive 1. 0.5 is positive 2. Oh, well, it's still a curve, but it's now in a different quadrant, isn't it? It was this quadrant. Oh no, we started graphing in this quadrant. Which one is the reflection? It is actually this quadrant. When we made it negative, it flipped it over and put it into that quadrant. And this quadrant here is going to flip over and go into that quadrant. Okay? It ends up being a reflection over the x-axis. Just by putting that negative sign in, you reflect over the x-axis. So let's show these this other branch down here. So if I go to 0.5, it's at negative 2. 1 is at negative 1. 1.5 is at negative 2/3. And 2 is at negative 0.5. And 2.5 is at negative 0.4. So there's the second branch of it. So what we're seeing now, we still have the two branches. I forgot H. I can't spell today. I'm sorry, guys. Branches. There we go. We still have two branches. We have asymptotes as well. And they follow the x-axis, which is y equals 0, and the y-axis, which is x equals 0. The domain remains the same. Even though it flipped over, it remained the same. So the domain was x cannot equal 0 because of that asymptote. And the range was y does not equal 0. Now, one thing to mention here is what did change. And what did change was the quadrants. So this one falls not in quadrant 1, but in quadrant 2 and 4. So 2 and 4. Or if I go back to my original list, this one fell in 1 and 3. This was the positive numerator, fell in 1 and 3. The negative numerator falls into 2 and 4. So it was a reflection over the x-axis that happened here. Reflection over x-axis. Or we could write that as y equals 0, the line y equals 0. Okay? Make a prediction for the next slide. What's going to happen when instead of it being negative 1 over x, it's negative 4 over x? Okay, so the next slide is negative 4 over x. Here are the points I'm going to plot. You can just throw it on Desmos and get a picture of it. That's perfectly acceptable. I do a negative, again, my negative sign didn't show up there. Negative 2.5 gets me to positive 1.6, which is there. Negative 2 gets to negative 2. I'm sorry, to positive 2. 1, 2, 2.6, 4 is all the way up here. So again, it looks like just by changing the numerator, in this case, making it further away from the number 0, stretches it away from the origin as well. Let's do the other branch, which I'm predicting is down here, because that's what happened the last time. 0.5, negative 8, I can't fit that on, so negative 1, negative 4. I'm sorry, positive 1, negative 4. 1.5, negative 2.6, positive 2, negative 2, and 2.5, and negative 1.6. Yep, it fell into that quadrant also. So it has the same asymptotes, the same domain and range as the last one, and the same quadrants. It's still falling in quadrants 2 and 4. Okay, so that's when we have the denominator is x to the first power. Now what we're going to do is we're going to change the denominator so it's x to the second power. Okay, so let's start with 4 over x to the second power. Go ahead and put that in Desmos so that you're looking at the same picture for when we go to do the characteristics of it. Okay, I'm going to put the graph up here. I'm still using 0.5 like I was doing before. And just like before, my negative sign does not show up on that too. All right, so negative 2.5, 2.5 is at 0.64. So that's right there. Huh. When I did over x to the first power, my first point fell down in this quadrant. This one's falling in this one. So I wonder if my two branches are going to be diagonal from each other like they were with the last one, or if they're going to be next to each other. That's a good question. I go to negative 2 and positive 1, negative 1.5, and 1.8, negative 1, and 4. All right. That's that one. Let's find out whether we're going to be in quadrant 1 or quadrant 4. So it says I'm going to go 0.5 and up to 16. Well, I can't fit that on there. 1 and up to 4. Ah, this looks like it has reflection symmetry. We'll go back and we'll talk about the symmetry of both of these also. So it looks like they're actually in adjacent quadrants. 1.5 and 1.8. 2 and 1 and 2.5 and 0.64. I always thought this one looked like a volcano. Okay, so again, we have two branches. We have asymptotes. And they are y equals 0 and x equals 0. Again, the x-axis and the y-axis. Our domain, same thing. X can equal 0. And our range is the same thing. Y can equal 0. Our quadrants have our reflections. So we do a little r. That stands for a reflection. And in the subscript, we put what line it reflects over, and it reflects over the y-axis, so it's x equals 0. You want to go back and add the symmetry of the last two. This one had rotational symmetry of 180 degrees. Now remember, we had some questions that had to deal with rotation and reflection symmetry, and that helped us answer the question as to whether something was even or odd. It still applies here. Okay, we're going to have to answer that question again. All right, so next up, what we're doing is increasing the numerator. Okay, so if I increase the numerator, I'm going to negative 2.5, and this time I'm going 1.28. Okay, and 2 goes to 2. And negative 1.5 is 3.6. So it looks like the same thing happened that happened with the x to the first power in the denominator. looks like it's stretching away from the origin. Let's see if it's also in quadrant 1. If I go over to 1 and 8, that won't fit. I go to 1.5, 1, 2, 3.6. Yeah, it looks like it's going to be in the first quadrant as well. I go 2 and then 2, and then 2.5 goes to 1.28. Okay, so it has the same characteristics as the last one. It has the asymptotes of y equals 0 and x equals 0. It has the domain that x does not equal 0, the range that y does not equal 0. It's in the first and the second quadrant, and it has reflection symmetry over x equals 0. Okay, we're gonna do a page basically that's gonna be like summarizing all of these pieces into one. So don't worry. Okay, so now we're gonna take it negative. The last time we changed from positive numerator to a negative numerator, it reflected over the x-axis. Let's see if that same thing happens with x squared in our numerator. So you can graph it on Desmos, much quicker than I'm graphing up here, but wanted you to see it actually come to life, basically. So I'll put my negative there again so I don't forget it. -1, 2.5, and -0.64. So it does look like at least this branch came over the x-axis. -2, -1, -1.5 is 1.8, and -1 goes to -4. So let's see if it still has the symmetry of reflection over the y-axis. Let's do 1 and -4. Oh, yeah, it absolutely looks like it does. And here, and here, and here. Okay, so we still have two branches. We still have asymptotes of the x-axis and the y-axis. We still have the domain is x does not equal 0, range y does not equal 0. This time we will change the quadrants because we now moved into quadrants 3 and 4, and it still has the reflection symmetry over the x-axis. The only thing that changed was which quadrants we were in. Well, that's not true. What did I do wrong on this one? I screwed up the range on this one, guys. I am so sorry. I hope you were yelling at me the whole time I did that. I screwed up the range. We don't have negative y values here. We only have positive y values. The y is greater than 0. That was on the equation 4 over x squared. We'll get it right on the summary page, I promise. And the reason I just got drawn to that is because I was trying to see something else that changed. And the range is another thing that changed here because we had a negative as the numerator. The y is not greater than 0 now. The y is less than 0 now. So those are the only two things that changed with this graph. And again, what's going to happen is we are going to actually see that increasing the distance, the number is from 0, so -8 is further away from 0 than -4 is. It's basically the absolute value is greater. It's going to cause it to stretch further away from the origin. So let's see, -1, 2.5. I have 1.28, right about there, I think. I go -2, -2. And then -3.6. Yep. So it's not as sharp a curve, basically. It's a much smoother curve going through. And then when I do it on this side, I can go, I can't graph that one. I can't graph that one. Let me start at 1.5 and -3, 1, 2, 3.6. And then this point, and then this point. I think those are the only three I really can fit on there. Okay, but you can see I still have the same asymptotes, still have the same domain and range as just the last slide. Y is less than 0 in this one. Still have reflection symmetry over the y-axis. I'm in the same two quadrants as the last one. Okay, so what we need to focus on when we were looking at all of those graphs together, when we saw all of the equations at one time like this, is the idea that these were positive over an exponent of 1. These were negative over an exponent of 1. These were positive over an exponent of 2 and negative over an exponent of 2. And you can see where this relates to what we were just doing last class with simplifying rational expressions, because these are rational expressions, okay? We have a fraction, basically, anything that can be represented as a fraction, and that's what these equations are, fractions. So now we're going to pull it all together into two summary pages, okay? Actually, are they the same? Yeah, one summary page. Not sure why I have two of the same. All right, so we've got two situations here. Up top, we get the equation. This one is over with x to the first power, and this is over x to the second power. So both of these are going to be to the first power, both of those to the second power. And in this row, we're going to make it so that the numerator is positive, and the bottom row, we're going to make it so it's negative. So, we sometimes mess up that inequality, so we'll write these words just to make sure. All right, so what this graph looked like, and I'll help you with the sketches of them, is it was in this quadrant, and it was in this quadrant, okay? So the domain was everything except for 0, so x does not equal 0, and the range was everything but 0. The asymptotes were the two axes, so x equals 0 is the y-axis, and y equals 0 is the x-axis. Now, to be even or odd, we talked about that a couple units ago. To be even or odd, even means that it is using the origin and that it has reflection symmetry. And odd means that it's using the origin and also has rotation symmetry. So even though we don't have a point going through the origin per se in this graph, it is actually centered on the origin. So we will consider that as being the origin being part of this graph. And because it has the rotational symmetry of 180 degrees, we're going to say that it is an odd function. And we are in quadrants 1 and 3. I think that summarizes all the stuff we had. Okay, let's stay with that linear one, but now let's turn it negative. What happened when it turned negative is this branch that was in 1 now reflects over the x-axis and moved into 4. And the branch that was in 3 reflects over the x-axis and moves up to quadrant 2. So my quadrants are 2 and 4 now. The domain and range stay the same. X does not equal 0. Y does not equal 0. I'm sorry. Yes. The asymptotes remain the same. X equals 0 and y equals 0. And this one is still an odd function because it has a rotation symmetry of 180 degrees. So that summarized all the ones that were over x to the first power. Now let's look at x to the second power. All right. When it was to the second power, it looked like this with a positive numerator. So my domain was at all x's except for 0, but my range was that y had to be greater than 0. My asymptotes are still the axes, so the y-axis is x equals 0, and the x-axis is y equals 0. Now, it's not odd because it doesn't have rotation symmetry, but it is even. We're still going to say that we're using this origin because it centers the branches, and it has that reflection symmetry over the line x equals 0. So it is even, and it is in quadrants 1 and 2. Then when we took our numerator and made it negative, it reflected over the x-axis and caused that look. So it is in quadrants 3 and 4. Domain remains the same as up there. X does not equal 0, but the range changed. Instead of being above the x-axis, we're now below the x-axis in the negative range. So all of my y's are less than 0. My asymptotes stay the same. And it is still even because it has a reflection symmetry over the line x equals 0. So that's a nice summary page of all the pieces that we picked up. And now we're just going to practice some things. So this is a great page that even if you didn't write down notes before or anything, if you're one of those ones that likes to take screenshots of things so that you have them for a reference for the quiz or the test, there you go. Okay, remember you can rewind and come back to it. So I'm going to go to the next page. All right, so basically what I want to do is I want to figure out which one of these graphs. Now these graphs have been translated off of the origin. You'll see that they're not really centered at the origin anymore. We're going to deal with the translations of these in a second. But we still have the same basic setup of a constant over the variable to the first power with the negative over the first power, and then the constant over the second power with the negative. So when I see the two graphs together, like this, the two branches next to each other, I know that it's going to be over x squared. And when it's over x squared, if it opens up like this, if it's in the top half, I know that that's going to be a positive k value. All right? See if you can write the equations in for the other 5. Pause it, and then I'll write them in. All right, so now I'm going to go ahead and write these others in. This one I know is going to be over x to the first power. But it looks like it is actually the reflection, so this looks like it's going to be a negative k. This is over x to the first power. This one has a positive k value because it ended up in the correct direction that we were thinking before. This one, same, we have diagonal branches, so that's over x to the first power, but it looks like it's a negative k value because it's switched which quadrants it would go to. This one, the two branches are next to each other, so that looks like it's over x squared, and it's going upwards. That means we have a positive k here. This one, the branches are next to each other, so we have over x squared. This time they're going down, so that means that we're looking at a negative k value. All right, let's test yourself some more with some translations. All right, so we want to, this is the original graph here, but we want to look at the translation. So I'm not worried about doing the original graph. We can go back and look at that. We know that it looks something like this, right? That's the original graph. All right, so if our new function h is equal to g of x minus 3, what this is telling me inside the parentheses is that I'm going to go 3 spaces. Remember, when it's with x, it's opposite. So I'm not going negative 3 spaces. I'm going positive 3 spaces. 3 to the right. Okay? All right, so that means my whole graph is going to move 3 spaces to the right. So instead of being centered at the origin, this is going to be my new center right here. So I keep this asymptote, but my new asymptote for the vertical moves over to there. So there's my translation of my graph. The new asymptotes are still y equals 0, but this time it's x equals 3. Okay? All right, let's look at another translation. Remember, that showed up in the parentheses with the x, so that's why it affected the location of the graph in the x direction. Okay, so this one here, we have that it's going to affect it in the x direction. It's going to move it over 2, so move it over, oh, but that's a plus 2. So that means we're going to go 2 to the left instead. So it's going to move it to there. Then it's got this minus 3 on the outside. That's going to affect the y direction. And we keep it as the same sign. So we want to move it 3 down now. All right, so from 2 to the left to 3 down. 1, 2, 3. Here is my new origin right there. So what that's telling me is my asymptote goes vertically through that origin and horizontally through that origin. It's almost like I'm drawing a new set of axes, basically. And my graph is going to be here and here. So let's look at those asymptotes as x equals negative 2, and my other one is y equals negative 3. Those are my new asymptotes. Okay, so pause here. See if you can come up with the new asymptotes and a picture of the graph for this one up here. See if you can get that on your own. Okay, what I see is it's moving 1 in the positive direction because I want opposites. So 1 to the right and 4 up. Okay, so if I'm moving 1 to the right, that means my new asymptote is x equals 1. Means my other asymptote is going to be y equals 4. So if I go from the original origin and I go 1 to the right, that puts me here for this asymptote. And if I go 4 up, that puts my other asymptote right there. So there's my 2 branches. Okay, we did those. I think I've got some repetitive slides coming up. I might just skip through them. I think they just repeat stuff that we've already talked about. Okay, I think we're good with the translation. Okay, if you're seeing it as an equation like this, you see how this 4 is with the x? So I wanted to actually move it 4 in the negative x direction, so negative 4. So it should be, and it's linear, so it should be one of these that go across from each other, right? That one, no, because that would have been a negative number in the numerator. And I only wanted to move sideways. This one looked like it moved up also. So I'm looking at this being the equation for that one there. This is also linear. And it looks like it's just going to move to the right, positive 2. So I'm seeing this graph right here. Okay, I have a squared graph right here. X minus 1, negative 2. Okay. So this one's saying it's going to move 1 in the positive x direction. And that's it. So I want it moved. That moved the wrong way. That moved down also. And these are my 3 squared ones. So it doesn't look like that's a possibility. So I'm going to cross that one out. This one says I want to move a positive 1 in the x direction. This would be these branches. It would have to be this one because that's all that's left. So do I move a positive 1 in the x direction and a positive 3 in the y direction? It looks, in fact, that is the case. So that means my other x to the first power doesn't show up here. So now let's make this one looks like all that happened. It's an x squared, and all that happened was I moved 1 in the x direction, but it should be a positive numerator because it opens up. I moved 1 to the left, and that would make that the opposite. So I'm agreeing with that one there. This one still opens up, but it looks like it's changing the x direction and the y direction. Okay, so I moved a positive 1, so that would be a negative 1 down here, and then down 3. Seems correct. This is also the squared, but the negative number reflected it, so that is correct. And it moved negative direction here of 1 and up 3. So that matches that graph right there. Okay, so there's some more ideas of translations for you. Okay, so I'm going to do this one slide, and then I'm going to set you to your closure. So we have, we're talking about x squared here, right? When you do your closure, you're going to be talking about the graphs that we looked at today. So I'm just giving you an example of how to answer these with a graph we already know. So it's saying that my new graph is going to change negative 3 in the x direction and negative 1 in the y direction. So I'm going to write an equation for that. So that means I put, instead of having the x there, I'm going to put x plus 3 where the x is. So that means I have x plus 3 quantity squared, and then I'm going to tack that negative 1 on there. And the transformation to get from one to the other is 3 to the left and 1 down. And the next one, I'm going to take x minus 4, substitute it in where x is. So that's going to be x minus 4 squared, and then I'm going to have the plus 5. So it looks like I'm going to be moving 4 in the positive direction, so that's 4 to the right, and 5 up. That's basically what I'm asking for with your closure. So what you can do right now is go to your closure and give it a shot. See if you can come up with a new equation and the transformations. Okay, and get that closure submitted so that you get your grade for today. Okay, we do have a quiz coming up on a Friday, so keep that. I'm going to go and look really quick at the dates for the quiz. So that's week 34. I think it's in week 35. Actually, I don't need to look there. I can look at this paper. I have it on. So the quiz will be on a Friday again, like we did last chapter. And it is actually falling on the 14th, okay? On 5/14 is going to be your quiz. So mark that down. All right. And then I guess I will talk at you at the next lesson.